Good afternoon, everyone, and thank you for joining Hosokawa's webinar on roller compaction and dry granulation technology for chemical applications. My name is Greg Boyer, and I'm the marketing manager for Hosokawa Micron Powder Systems. Hosokawa Micron Corporation is a global leader in powder processing equipment and systems with headquarters in Osaka, Japan. We have over 1,500 employees worldwide, production facilities in 5 countries, and 12 technical centers and research facilities. Hosokawa Micron Powder Systems was founded in 1923 under the name Pulverizing Machinery. We design, manufacture, and assemble equipment for size reduction, classification, mixing, compaction, and laboratory analysis in the North and South American markets. Our equipment is designed for chemicals, food, pharmaceuticals, minerals, cosmetics, and plastic industries. We have a research and test facility complete with analytical laboratory in our Summit, New Jersey office, where we encourage our customers to join us for trials and system evaluations. At this time, I'd like to introduce our presenter, Leo Heinrichsmeyer. Leo has an extensive experience in chemical and pharmaceutical compaction applications. He has worked for Hosokawa for over 15 years and was responsible for the successful development and installation of more than 300 compaction systems worldwide. With a master's degree in mechanical engineering from Paderborn University in Germany, he is considered Hosokawa's expert in compaction and also Hosokawa's expert in socket. Leo?
Thanks, Greg, for the introduction. Thank you, everybody, for joining us. There are a lot of registrations from people who work in the pharmaceutical industry. Therefore, we add some slides at the end, giving some information about equipment for dry granulation. Before we come to the compaction, I'd like to give a definition about compaction. Roller compaction is the densification of dry powders into a solid mass, the flake. This densification process is achieved by controlled feeding of powder through a set of directly opposed counter-rotating rollers. For granulation, I found something in Wikipedia. Granulation is the act or process of forming or crystallizing into grains. Granules typically have a size range between 0.2 and 4 mm, depending on their subsequent use. Transferred in our process, we use the term granulation for crushing the flakes into granule size. Talking about briquetting. The word itself sounds a little bit like brick, which is a single, solid, and hard piece. Briquetting is the densification of dry powders into a single, solid briquette. The briquetting process can take place with or without binder. The binder can be liquid or powder. For briquetting in a roller compactor, we can add that densification process is achieved by controlled feeding of powder through a set of directly opposed counter-rotating rollers. The densification factor describes the ratio between the volume of the material before and after compaction. The volume of the material is fed to the compactor is a function of the rolls. Of the tools, the material and the process. It is the same for the material which comes out of the roller gap. So you can see that here. In case we do not change the material nor the tools during a run, the functions are much more simple and can be seen as the volume fed into the roller gap, which is a function of the process. The volume which gets out of the roller gap can be seen as a function of the process too. Going more into detail of how the volume of the material which is conveyed into the gap can be influenced, we see that it can be done by the feeding auger and its speed. So this is here. For the volume of the material leaving the machine, we have only the speed of the rolls and the gap between the rolls. So you can see that everything, when we put it together, is a function where we have only left here the screw speed, the roll speed, and the gap. And everything itself can be seen also, which is a little bit like the pressing force. So the pressing force can be used to control the quality. The densification factor describes the ratio between the volume and the material before and after compaction. A hydraulic system always creates an external force to keep the rolls together. The compaction force is always created by the material. In larger roller compactor, one roll is designed fixed and the other one is equipped with a hydraulic device. In case the compaction force is smaller than the hydraulic force, H, the gap will be at the minimum. In case the compaction force F is bigger than the hydraulic force, the gap will increase until the compaction force F is equal to the hydraulic force. The system acts like a self-control. The hydraulic never creates a pressing force. It only limits it. The compaction process can be divided into 3 zones. In the first zone, the material slips still a little bit on the roll surface, and only small stresses are acting on the material. The product starts to degrade. The pressing force in this zone is 0. In the second zone, the material doesn't slip anymore. The material deforms plastically under heavy stress performed by the rolls. The so-called nip angle is defined at the point where the material starts to move into the nip. Compaction takes place in this zone until the neutral angle is reached. The pressing force increases from 0 to the maximum value. In the third zone, the material expands because the pressing force is reduced to 0. Due to this effect, the material speed is faster than the roll speed. The pressing force is reduced from the maximum value to 0. Inside the different zones, the following happens. In the entering zone, the material starts to dense. The small particle starts to move into gaps between bigger particles. Inside the compaction zone, the material moving process goes on. In case the feed material contains not enough fines, it will be created by pressure and friction. The pressure inside the flake reaches the maximum value and the maximum density. The bonds are created. In the exit zone, the material releases the roller gap. The pressing force is reduced to 0, and the flake expands again. In the exit zone, the flakes and briquettes were released from the roll. So after taking the pressing force from the material, it will expand like I told you before, and this effect is related to the Young modulus of the material. So the Young modulus, which is the tension divided by the strain. But it's also something that too high forces will destroy already activated bonds. So this effect we call the overpressing effect. Here on the next slide you can see in the first picture a flake, and in the second one briquettes, where we have this so-called overpressing. So in the upper picture you see what I call always the fishbone structure. And in the lower picture, you can see something which looks a little bit like something we know from the 80s. It's the Pac-Man. So both effects happen when you start overpressing. When you don't want to have this effect inside, you have to reduce the pressing forces. All pressing forces will apply to the material near friction. In the easiest compactor, which has only gravity feeding, the part of the gravity force which acts rectangular on the surface on the roll works as a normal force. The friction force is equal to the product of the friction coefficient and the normal force. You can see this here. At the same time, the already densified material will expand. So, to achieve high throughput, the compaction zone shall be as large as possible, which means also you can increase the speed of the rolls as high as you want. So there are some machine parameters which helps you to increase the nip angle. One is a rough roll surface or forced feeding. So most of modern compaction machines do have a forced feeding system, mostly with a screw feeder. Also a low roll speed increases the nip angle, a small gap, and also a low pressing force. In the exit zone, the material expands. There will be a relative movement between the flake and the roll. This is not critical for normal products, but in case of abrasive material, high wear occurs. The roller gap influences the throughput. Due to the elastic expansion, a larger gap also increases the time for the material in contact with the rolls. In case of too large gaps, the flake or briquette can stay in the pocket of the roll. In the upper part of the picture shows the distribution of the pressing force in case of gravity feeding and flat roller surface. This is also known as the pressing force distribution according to Johansson. In the lower part, the pressing force is shown as a function of the width of the rolls. At the edges, it is zero. In practice, we work with a feeding auger to increase the compaction zone. So this is what you can see here. By using a feeding auger, a sine wave will be applied on the roll, which is caused by the last blade of the feeding auger. For better understanding, it can be explained that the powder material is more elastic than the last blade of the feeding auger. The real pressing force can be seen as a superposition of all three effects. Powders with fine particles contain a lot of air. This air has to be removed during compaction. Removing of air always works by moving of particles. Therefore, a force has to be transferred to the particles, which is responsible for the movement. The picture shows a model of how a force is transferred to the particles. An initial force F works on a particle which lays on three other particles. For every particle, the balance of forces is equal in x, y, and z direction. The picture shows that due to this effect, the forces will be reduced on the right side by every contact they have. The second effect is in removing of all air with these particles which are acting like a filter. The removal of air through a very fine filter is harder than a coarse filter. In case of recycling of fines, for tabletting, the material which is less than 200 micron will be recycled and fed back to the compactor with the virgin powder. In most cases, the virgin powder has a D50 of 10 to 50 micron. In case the number of particle-particle contacts are reduced by using recycled material. This effect is also often used in pre-granulation before tabletting in the pharmaceutical industry or in any other tabletting machine. As an example, pressing of hard metal plates for drilling equipment, pressing of special ceramics. The effect of easier venting by using coarser material is used also in the production of technical glass to reduce the amount of bubbles inside the glass. An easier example for this effect can be seen when you densify the ground before making a patio. You start with coarse material and go finer for the top layer. In most applications, a certain amount of fines is required to fill the gaps between larger particles. In case this fines is not part of the feed material, it has to be created by friction and compression. The compression and friction require a part of the energy, which is the total pressing force. To use more of the total pressing force, a wide particle size distribution, lubrication of the feed, and recycling of the fines are proper methods. In case of very light material, the efficiency of the feeding screw is very low. A vacuum deaeration unit can be used to increase the bulk density of the powder a little bit to have a better efficiency. In practical use, materials with a bulk density of 200 gram per liter and lower can be compacted very well with this technology. Densification rates of 10 and more can be achieved. A second effect of the vacuum deaeration is the reduced amount of air inside the product. The air of the feed material is released through the gaps between the roll and sheet plates. Due to the high speed of air, a certain amount of fine material will be taken with the air and leave the rolls without being compacted. In case of vacuum deaeration, the speed of the air in the gap between the rolls and sheet plates is reduced, and the amount of fines is reduced as well. On the other hand, the roll speed can be increased. There are different reasons for compaction or briquetting of powders in the chemical industry. The most common reasons for this production step are that low bulk densities are expensive during transport. Some materials are hazardous, so dust shall be avoided. Powder will stick together in a silo and cause serious storage problems. The following production step requires a dust-free material like calcination, melting, and others. Compaction is a cheap process for granulation of powders to granules, which requires approximately 10 kilowatt-hours per ton as energy consumption. In most cases, this is not necessary to add any further binder to the material. Adding of liquid binder or lubrication is not necessary, so we have still the pure chemical after compaction. Because of low speeds, the abrasive wear is very low. So we come now to a few examples for compaction and briquetting technology in the chemical industry. Sodium cyanate is a very hazardous and reactive material. Briquetting of the material reduces the surface area of the product. It can be stored much easier and the reactivity is also reduced. The next example is the briquetting of kaolin. During the calcination process of the material, it reacts under high temperature with oxygen. In the industry, this process is very often made in very large kilns. To obtain a good result, a homogeneous distribution of the gas stream is required. Therefore, the material needs to pass through by the air stream easily. The briquette fulfills this demand. The reason for compaction of uran dioxide is that it is a pre-step before tabletting of nuclear fuel rods. This material is very abrasive and unlubricated. The particle movement for compaction causes a high amount of friction. The compactor does not have so much abrasive wear like a tabletting machine. The compaction technology is required in case the addition of lubrication like stearates is not possible and a certain strength in the tablet is required. Like uran dioxide, a lot of catalysts are very unlubricated too, and cannot be tabletted to catalysts directly. Because of the two-dimensional movement of the rolls, the compaction in a roller press is more gentle than the one-axis pressing in a tablet press. The positive effect of pre-compaction can be seen similar to the model with the forces. So, you can see also the influence of the particle size distribution. On the picture, there's a plan for compaction consisting of a compactor, a pre-crusher, a fine crusher, a screening machine, and a vacuum conveying system for recycling the fines. The pre-crusher is required because the wire in the fine crusher is very thin. Because of pre-crushing, the lifetime of the fine crusher screen can be extended. The briquette mixture is very abrasive. Because of compaction, pressing force in the tabletting machine can be reduced. This reduces the abrasion in the tabletting press because the pressing force in the tablet press can be reduced to achieve the same density. During the micronization stage of toner, ultrafine particles below 5 micron are generated. These undesirable ultrafine particles create problems in the document imaging process. Additionally, this product cannot be reused in the extruder again in high quantities because of its low bulk weight of less than 200 grams per liter. The compaction process allows the reuse of ultrafine fraction in the extruder and up to 100% inline recycling of the material. Granular salt is required for easy casting of the material. When salt is mined, also a lot of fines is created. This can be used as well. The second advantage of the compaction process is that in case of salt mixture with special advantages, for example less corrosive, is produced, that every single grain contains the right mixture of salt. There are different tests we can make on the material before and during a lab test on compaction or briquetting. The most important one is the Piston Press test. It is an initial test. It is used for testing the compaction behavior of a material. With a very small amount of the material, the compaction behavior can be tested. After that, the density of the tablet can be measured and also the strength. During lab tests, the particle size distribution of the feed material and the granules can be measured. Therefore, an air jet screen will be used. The density of the flake or briquette is important for the quality. It influences throughput and also the hardness. The bulk density depends also on the density of the flake. For measuring the density, we follow the Archimedes principle. This is a simple method which can be carried out in a few minutes. The bulk density is important when the material needs to be packed in bags or reduce the transport cost. In our lab, we can measure the packed and loose bulk density in the Hosokawa Micron powder tester. The strength of briquette is important for the handling because it should be resistant during the transport to the place where it is required. For the shatter test, a sample of the briquettes will be dusted by screening. After that, it will be thrown from a height of 2.5 meters several times on a steel plate. These results can be given like first fall from 2.5 meter, 95% bigger than 10 millimeter, and second fall from 2.5 meters, 90% still bigger than 10 millimeter. The strength of briquettes can be measured also with a hydraulic press. Therefore, the pressure of the briquettes will be increased until it breaks. Two different modes can be used for measuring pressure and break resistance. So, as I promised, now a little bit for our friends from the pharmaceutical industry. For pharmaceuticals with a high amount of API, such with a low biological disposal, like blood pressure dropper, very often compactors with a low to medium throughput capacity between 50 and 300 kilograms per hour are used. Cleaning is done in a separate cleaning area. Typical for this system are a low-medium throughput capacity, variable batch sizes, multiple products, cleaning and high quality of compaction are the most important issues. For good and easy cleaning, these systems are mobile. All the cables can be disconnected easily. The heavy parts will be taken by a forklift. So you can see that, for example, here. And here you can also see that everything is splittable. These installations are one-floor installations. For pharmaceuticals, with a low amount of API, such pharmaceuticals which contain very hazardous or multi-component API, very often compactors with a low throughput capacity between 50 and 120 kg per hour are used. The systems for not so hazardous APIs are very similar like the small throughput systems for the high APIs. They can be characteristic with low throughput capacities, small batch sizes, multiple products, and that cleaning and high quality of compaction, less as possible contaminations are the most important issues. For very hazardous API, machines inside a containment are used. Like shown here in the picture, the protection of the operator has the highest priority. Cleaning and avoiding of cross-contamination are as well very important. Cleaning will be done inside the closed containment. This picture is a good example for what we can offer to our customer in case the standard design cannot meet their requirements. Special materials and special coatings on the machine based on our standard. For briquetting of charcoal, we have a low pressure version because the briquetting of charcoal does not require so much pressing force. Here you can see a roll tire of a briquetting machine with almond shape. The throughput of this machine is about 10 tons an hour. These rolls are designed for very abrasive materials. They are hard-faced with hard metal. Here you can see a standard roll tire which is used for compaction. A smooth roll tire which is used for high-pressure roller grinding. A roller compactor with gravity feeding. The sliding gauges here at the side are for adjustment of the flow. This shows the standard feeding device with a conical hopper and one feeding auger. Here you can see a multiple feeding system for compactors with wide rolls. A feeding system with a combination of horizontal and vertical screws. So during the last minutes we talked about the theory of compaction, the different forces which act on the particles to perform the bonds. The stages of compaction in a roller compactor were described. Special solutions like vacuum dilation were explained. Examples for compaction briquetting were given. There are different ways to determine the quality of the compaction and briquetting. An overview of the measuring systems was given as well.
Thank you, Leo. At this time, we'd like to begin our question and answer session. From the look of it, we've received quite a few questions here, so we're going to do our best to get to all the questions. However, if Leo is unable to answer your question during this live program, he will respond to you offline. Yeah, Leo,
So we just received the first question. Why will some material pack inside the feed screw? Are there any solutions to material packing inside the feed screw? So with this I have to explain that every material has a pressing force where the bonding mechanisms start. In case these forces are very low, it can be reached also in the screw. In this case, the forces in the screw have to be reduced or gravity feeding has to be used. Sometimes the solution is to change also the surface of the roll. In most applications, coating of the screw will not work because of abrasion. In case this does not satisfy you, you can see also my email address. Please send me an email. We just also received the question, do you have any application in cosmetic products where the product is very cohesive and very low flowability? In the cosmetic production, we have not so many applications. Compaction is always an intermediate industrial process, and so in the cosmetic industry, I know that, for example, powders are the end product. So I do not know any of these processes, or not at the moment. So also in this case, I would like to ask you to contact me later on with more information, which we cannot handle here at this webinar. There's another question of how we decide whether we need a binder or not. This is also something this customer also wrote that he has interest about coal. So coal not always is able to compact to so hard briquettes like you want to have it. For charcoal, it is very easy. Only a binder can be used, which during burning will not destroy the meat you have on your barbecue grill. So in this case, a binder is used, which don't do that. In case we are not able to create high enough bonds, always a binder needs to be used, and it's only the question, what is the right binder? Is it something which is organic or inorganic? There's a question that I described some operating parameters that would change the nip angle of the process. And if I can explain more about that, there's one thing. The nip angle is a theoretical physical parameter. So we only can see that it is changed. You cannot measure that. So by increasing the nip angle, for example, the material flows better into the rolls. That means when we use a very high speed of the rolls, the nip angle is normally not so good. So all materials have a limited maximum roller speed. And that means if the nip angle is too bad, the material will not go into the nip. There's a question, are there any significant differences between compaction of metallic powders versus non-metallic powders? Of course, first of all, metallic powders have in most tests, they have much higher bulk density than non-metallic powders. So the bulk density is one big difference, which helps the material to go better into the nip of the rolls. On the other hand, also the flowing behavior of most metallic powders, even if it's 100% metal, is much better. Metal oxides have normally very high pressing forces. It's always a question, do we talk about pure metal, metal oxides, or any salt which contain metal? So we just look for further questions. There's a question from our friends from Israel. How do we choose between the different granule shapes? So the granule shapes, it is difficult to understand what you mean with that question. So after compaction and granulation, we have normally an irregular shape of the granules. When we talk about briquetting, it is in most cases that the following step will influence also what we try to achieve on the briquetting roll. So it's in most cases a customer demand. There's a question, if the process generates heat, and if yes, how much roughly? That depends on the material. So we talked also about lubrication and also about friction. Friction always creates heat. So when we have a material which is very unlubricated, the amount of friction inside the compaction process is much higher than with the lubricated material. So this question, I have to say, it's always depending on the material. There's a question of the experience in briquetting a mixture that was designed to disperse upon submersion in water. During the compaction process, we press the material together. So it depends always what is the problem with the mixture or with the briquettes, which shall be dispersed in water. So for example, when you have a powder with a very high surface, it can happen that it swims on the water surface before it's able to be wetted. In case this is a problem, compaction and also briquetting helps for the dispersing. But on the other hand, this dispersion itself will be slower. There's another question of how moisture affects the compaction capabilities. So it depends also on the material. If you have only a little moisture inside the product, it can act like a lubrication. If the moisture content is too high, we will come into an hydrostatic pressure, and then compaction will not be possible anymore. And this also depends on the material. For salt, it is different than for kaolin and also other materials. There's another question for a roll with briquetted pocket. It is advantage to have the column of pockets offset from each other or lined up. It depends. When you want to do compaction, I prefer always one line, but it sometimes makes sense to, let's say, having natural cracks in the total ribbon where the material breaks easier. And then it makes sense to have several pockets. In any case, it's harder for a material to enter, let's say, multiple pockets to the side of the rolls than for a lined up pocket. And therefore, I try to use always a lined pocket. There's another question. How would you measure the granule density of the granulated powder? Of course, this also depends on the powder itself. Normally, I would use also the Archimedes principle. So take a little amount of material. Of course, it's always a question about the right liquid which you use for measuring. I prefer a mineral oil. First of all, the viscosity is very good to measure everything. It depends also on the density of the granulated powder. So that means if the density is below 0.87 kilogram per cubic decimeter, it will not work. So it really depends on the material. There's a question regarding the optimum moisture content for salt. First of all, if we have moisture inside the salt, it can cause trouble later on in the process as well. So I would try to be at 0.1% and lower. In case normally you try to increase the moisture content for salt as much as possible. So it depends also a little bit about the environmental conditions. The lower the content of moisture inside the salt is, the better the process will be, in case you avoid the problems in compaction, but also in classification later on with the screening machine. There's another question for good compaction. What should be the percentage of granule density compared to the density of pressed product? This is a very easy answer. It's normally around 50%. So I understand granule density as a bulk density. So the loose bulk density is the density of the 50% of the pressed flake. If I did not understand the question correct, that you mean with the granule density comparing to the density of the flake, then it's 100%. There's a question. Is there a minimum critical size of metal powder to get a good compaction without binder? That depends on the material. So there are some metal powders which are easy to compact, others are not so easy to compact. Also, regarding this question, I would like to contact me after this presentation, because we have to go more into detail with the material. There's a question from some customer in the pharmaceutical industry. Can roller compaction reduce the stickiness of the powders? It can do. Stickiness also is related to the surface. And by roller compaction, we reduce the surface area of the material. So instead of a lot of contacting points with very less weight of each particle, we have later on less contacting points and also much higher weight of each granule. So the stickiness of the powder can be reduced. You can see that also as a practical use when you look at cat litter. There's normally a typical size because some of these very expensive cats have very long hair, and the cat litter shall not stick on the long hairs. And the other thing is when a woman uses some cosmetic colors in her face, it's normally a very fine powder. There's a question regarding the briquette size of I think we are talking about sodium cyanide. What is the smallest size of briquettes where sodium cyanide can be produced, and can they be further used for tablet compression process? Normally, this is not possible with the briquettes. In this case, the briquettes will be crushed to granule size, and they can be used for the tabletting compression process. So I will answer one last question now, because we are late in time. So there's a question regarding the compaction process, raises the material temperature. For example, in the pharmaceutical industry, for example, with heat-sensitive vitamins. Also in this case, we can, for example, say normally cooling of the rolls is not the right thing, because it's not possible by cooling of the rolls to reduce the temperature to a certain limit. The reason is very easy to answer, because the contacting time for the material with the rolls is only a quarter of a revolution, and the area is limited too, so we have a quarter of a revolution multiplied by the width of the roll, and also the temperature difference between the rolls and the material is not so high. Normally you use only chilled water, which will have maybe 10 to 15 degrees Celsius. In these cases, we normally use only the stearate to reduce the friction inside the material.
Thank you, Liam. And we'd like to thank all of our guests for joining us today. We know there's still a lot of questions that are being submitted at this time, and as we are running out of time, Leo will contact you offline to provide you with a complete response. Today's program has been recorded and will be posted to the Hosokawa website in about 48 hours. Please feel free to review the program again and share the presentation with friends and colleagues. If you have any questions about the presentation or this technology, please feel free to contact Leo directly with his contact information posted above. Thank you so much.